Alright, today's lesson is on 13B and C, lines in 2 dimensions and 3 dimensions, finishing up what we started on Friday, and also adding the one concept from 13F regarding whether or not objects in motion along these lines actually meet. It's just one additional concept here we'll add in. Before we get into the lesson, however, let me just explain. In order to shorten this video, I have the completed work and everything here, so you'll be able to see that. If you want to write it down as you take notes on the video, you can pause, of course, but I'm just going to go through and explain and make the video shorter in that sense. Before we get to this, I want to look at one example from the homework problem, and that is, here we're asked to find points, plural, on the line with these parametric equations that are 5√3 units from the point 1, 0, -2. Okay, now when you're talking about units from a point, what we're talking about is magnitude. Okay, so what I've done is I've constructed this generic point x, y, z using the 3 parametric equations. So my x coordinate is 2 minus t, my y coordinate is 3 plus 2t, and my z coordinate is 1 plus t. Then what I'm going to do is find the vector between that point and the point 1, 0, -2. Now it doesn't matter which direction I make this vector, because all we're concerned with is the magnitude. And that's going to be the same either way. Now, what I am going to do in order to keep the coordinates for this xyz point positive is I'm going to make my vector go from the xyz point, or I'm sorry, from the point 1, 0, -2 to this xyz point. Because when you get the vector between 2 points, you always take the coordinate of the point you're going to minus the coordinate of the point you're going from. So, as I write this vector, I'm going to have 2 minus t minus 1, and 3 plus 2t minus 0, and 1 plus t minus a -2. Okay? So you'll see what I've done here. Here are what I just gave as the components, and I've then put those into this magnitude formula. Okay? So I have the square root of my x component squared plus my y component squared plus my z component squared equal to 5√3, because that's the distance we want. Now it's just a matter of solving this. I'm going to run through the algebra real quickly, but really the key part here was getting this set up. Stating this generic xyz point, finding the vector from that point to the given point, or I should say in our case from the given point to the xyz point, and then plugging those components in to our magnitude formula. Of course, at this point I would need to square both sides, FOIL out everything on the right hand side, do all the algebra, and I get an equation 0 equals 6t squared plus 16t minus 56. I divided everything by 2 to get 3t squared plus 8t minus 28. That gives us 2 times. Okay, and the reason why we have 2 times is because we have this line, and we have the point, and the distance is going to happen twice. Unless we happen to have a point that's exactly perpendicular at this distance 5√3, which this one is not, we're always going to get 2 results. We'll get 5√3 on this side, and we'll get 5√3 on this side. So one of these is at time -4 2/3. The other one would be at time 2. Then all we have to do is plug in those 2 times, and we'll get the coordinates of the 2 points that are that distance away. So once we get it set up, it's a relatively simple process. It's just a matter of making sure you set it up correctly, get that vector written right, and plug it into the formula for magnitude correctly. Okay. So now, going from there to what we spent the majority of our time on today, remember that we have three different ways of writing the vector. The vector equation, having the vectors actually written as vectors in it. Then we have the component vector form where you actually see the starting position vector, and then you have here your velocity vector. And then of course we can write those in terms of our parametric equations where each component has its own equation according to the parameter of time that we have present in all three, but here we're writing each component as a function of that parameter time. Okay. Now, the applications we want to look at today are the intersections of these lines, and to start out with, the angle at which these lines intersect. Okay. Now, what are we talking about? I have two lines here, R and S. The vector equations in component form. Notice they're in 3 dimensions. Here's my starting position vector for R is 12, negative 15, 15. The parameter t, and then I've got negative 2, 3, 1 as my velocity. And then you can see the same parts there for S. But you'll see what we have is, let's just say, for the sake of our example, that this one's R and this one's S. Anytime you have two lines intersecting, it's going to form one obtuse angle and one acute angle. And just by a matter of habit, when we're asked for the angle between two lines, we always give the acute angle. Okay? Now, if this were just two vectors, if all we were looking at were the velocity vectors, then we would, if it were obtuse, we'd leave it obtuse. Because we're just looking at two vectors. But in this case, we're looking at the entire line, so we have the choice, and we're always going to choose the acute angle. All right, so how do we find the angle between the two lines? We have to consider what is causing them to go at the angle that they're at, and that is our velocity vector. That's the one that impacts direction. So what we're going to do is find the angle between those direction vectors, or velocity vectors. Okay, you remember your formula here, u dot v over the magnitude of u times the magnitude of v equal to the cosine of theta. You can refer to earlier lessons as to how to get dot product and magnitude, but we're going to use negative 2, 3, and 1 as our u, and we'll use 1, negative 4, 5 as our vector v. And we get u dot v to be negative 9. The magnitude of u is root 14, and the magnitude of v is 1 plus 16 plus 25, that's 42 square rooted. So we have root 42. Now, when we punch that into our calculator and get theta, our calculator is going to give us 111.8. Of course, that's the obtuse angle. That's this one right here. Okay? So we then subtract it from 180 to get the acute angle, and this is the angle we're really looking for. That's 68.2 degrees. Okay? So that's one application. Now, one thing that you need to understand here is that in 2 dimensions, unless the lines are parallel, they're always going to intersect, right? What you may have in this case, and we don't know because we can't see these in space, but these 2 lines may not actually be intersecting. Okay, as you look at it, R might be kind of closer to you than S, so it appears as though there's an intersection, but they're actually what's called skew. They're not parallel, but they're not coplanar. They're not in the same plane. Alright, so while we can look at it and see what there would be if they were on the same plane, and we can see this angle of what they would be on the same plane, in reality they're skew lines and they're not intersecting, okay? But we can still find the angle between them if we pushed them together to where they were intersecting. Now, on the topic of intersecting lines, let's take a look at how we would find the intersection of two lines. Okay, so here we have two lines with their vector equations. First one, xy equals negative 2, 1 plus s times 3, 2. And line 2 is xy equals 15, 5 plus t times negative 4, 1. Now, notice here we did use two different letters for our parameters. And that's because these two equations aren't bound to each other in any way. So to avoid confusion, we use two different letters for the parameters. But you'll see we have two different velocities, the velocity of 3, 2 for our first line and the velocity negative 4, 1 for our second line. So in order to figure out where the two lines meet, we want them to be at the same point. Okay, so we're going to set these two equations equal to each other. All right, we want this to equal this. So that's what I have here. Now obviously we have two variables, s and t. So what we're going to do is we're going to actually rewrite this vector equation as a system of equations by looking first at the horizontal components, or our x's, and notice if I pull just those out, I have negative 2 plus 3s equals 15 minus 4t. I've taken just the horizontal components of each vector and I formed this equation using those in our parameters. I do the same thing for y and I get 1 plus 2s equals 5 plus t. And now I have a system of equations that you can solve a number of different ways. However you've learned to solve them in the past, you can use whichever valid method you want. I chose to multiply this entire second equation by 4 in order to eliminate my t's. So I have negative 2 plus 4 is 2, 3 plus 6s is 11s, 15 plus 20 is 35, and then of course negative 4t plus 4t is 0. So I've eliminated my t's. From here, it's a pretty simple process just to find that s is 3. Okay, and then if we plug t in, that s into either of these equations, we can figure out what t is. So we either have negative 2 plus 9 is 7, 7 minus the 15 is negative 8 divided by negative 4 is 2, or you have 1 plus 6 is 7 minus 5 to give you 2. Now, we don't know the intersection point yet, but we do actually know one thing about these two, and that is while their paths will cross, because we have different times, they're going to cross paths, but they're not going to actually meet. The two objects that are moving along these lines, because the times are different, they won't actually meet. All right. But we can still figure out where they cross paths. We're going to plug in S to line 1, or we plug in 2 to line T. Either way, we'll get the point where they intersect. All right, so you'll notice here, if I plug in 3 for S, I get the 0.77. If I plug in 2 for T, I get again the 0.77. So that's where these two lines are going to intersect. I didn't have to do both, but doing both does ensure that we actually did our algebra right and do have the right answer. The last thing here is when we have two lines in 3 dimensions. How do we figure out if they intersected and whether or not they meet? Okay, so I did a little variation of R and S from before. And the question is, do these lines actually cross? And if they don't, then they would have to be skew. And if they cross, do they actually meet? Now that's going to be easy to figure out because if they meet, then we're going to get not only a point the same, but we're going to get the same time. All right, so we're going to follow a similar process to what we did. We would set these two equations equal to each other, and then I would write, in this case, three equations, one for x, one for y, and one for z. All right, and you can see those three equations here. So we have three equations, but only two variables, t and s. So I just need to pick two of them and solve for t and s. Then we'll use the third one to double check, and you can kind of see that already there. All right, so what I chose to do is multiply the first equation by 4 so I can eliminate the s's. I do that. When I eliminate the s's, I get 33 minus 5t equals 18. That gives me t equal to 3. When I plug that 3 in, and this is where you can use the z to double check as well, when I plug t equals 3 in, whether I plug it into the x or the y, or as you can see, plugging it into the z, you should get the same s. Now, it doesn't have to be 3, but you should get the same s from all three of your equations, x, y, and z. In this case, we did get 3, and that means that these two lines, these two objects actually met. So they didn't just cross paths, but they actually are going to meet. And now we can figure out where they meet by plugging in 3 for s or 3 for t. When we do that, again, if we do it to both, we can double check to make sure we did things correctly. We get the result 6, negative 6, 18. Okay? Now again, these ones happen to meet, so s and t were the same value. If we had gotten a different value for s, that would have been okay as long as we got the same value from x, y, and z. Alright, if we had gotten 4 for s in x, as long as we got 4 for s and y and z, they still would have crossed paths, they just wouldn't have physically met. So that's the basic concept here between intersecting lines and angles of lines as well. For intersections, set the two lines equal to each other, get your system of equations, and then solve it. And always, of course, find the actual point and double check your work. Alright, so that's the lesson in a nutshell. Here's the problems for the day, and hopefully this was helpful.